Thank you so much for attending this session. My name is Namrata, and I'm the co-founder of ShiftEco. And welcome to the workshop on Introduction to Life Cycle Assessment. So just to give you a background, this session is organized by ShiftEco as well as the Umbrella Institute. And the whole aim of these sessions is to talk about pertinent aspects of sustainability and trying to help you decode some of them. We've done something that we call business sustainability talks with a lot of sustainability leaders in the Middle East. And now we've started a workshop series. This is the first of the workshop series where we're going to talk about life cycle assessment. And then we have another workshop coming up, which will be run by the very talented Anne-Marie on the 30th on climate emissions, on carbon emissions. So without further ado, I want to take this opportunity to introduce you all to Dr. Deirdre Wolf. She has extensive experience in life cycle assessments. She has conducted a lot of LCA studies on a variety of innovative technologies, specifically in the energy sector. I think it's best if I let her introduce herself and kind of take it from there. Over to you, Deirdre.
Sure, thank you very much. Thank you very much for having me today. Yeah, so as you said, I am working mainly in the area of life cycle assessment and have conducted different studies in the area, and I have my PhD, which focused mainly on uncertainty management and life cycle assessment. So this is something that we won't really dive into today. We will keep it into an introduction and looking at the basics of LCA. So let me just share my screen. I mentioned that today we're going to focus on an introduction to life cycle assessment. And this is really a focus on kind of the basics for life cycle assessment. So we won't get too advanced today. So we're going to some key takeaways for today. Let me, admit this person, are that we're going to define life cycle thinking and life cycle assessment. We are then going to have a look at some of the international guidelines and product-specific standards that there are, and then go through the steps of a life cycle assessment using a case study example that I also used for my PhD thesis. And the overall thing as well that I want you to take away today is also understanding some of the key challenges of life cycle assessment. And holistic view, this is a good word. Thanks, Namrata. Great. Good. So from cradle to grave, end to end, so good. So we have some terms here coming up. So we have some familiarity with life cycle thinking. So really life cycle thinking, what we're looking at is really, it looks at the thinking that our choices also influence a larger system. So like you said, it takes a holistic perspective, looking at the life cycle of a product. So from the extraction of raw materials, the design and production, packaging and distribution, the use of the product, and then some disposal scenarios, whether you have some recovery, recycling of materials, components, reuse of some components, or disposal to incineration and landfilling. So this life cycle perspective can also take a viewpoint on all pillars of sustainability, so environmental, economic, and social. And it also looks at basically avoiding burden shifting from one stage to another or from one impact to another. So what does this mean? So say, for example, you have a product that you are looking to reduce its energy consumption during the use phase. So you might do this, look at reducing this energy consumption, but to do this, maybe you need some more electronic components. And then while you're reducing its impact on the use of energy, climate change, you might be also increasing the amount of metals, minerals that are needed for electronic components. So it's kind of looking at a holistic perspective. Also for life cycle assessment, so what do we mean by this? Well, this has different factors. So environmental, social life cycle assessment, environmental life cycle assessment, as well as life cycle costing. And there's also then the combination of the three, where you can have life cycle sustainability assessment. And what does it do? Well, it quantifies the potential impact of a product system over its entire life cycle, so including raw material extraction, production, manufacture, use, and end of life. And why do we do this? Well, LCA results are really used for decision making, and they have been increasingly used then also to inform policy development, with the overall goal that what we're looking at doing is reducing the impact of a product across its life cycle. So today we're going to focus on environmental life cycle assessment. So if you see life cycle assessment from here forward, what I'm talking about specifically is environmental life cycle assessment. And what this looks at then is you have the compilation of the inputs from the environment, so raw materials, energy, water, as well as the inputs throughout each stage of the life cycle assessment, and their evaluation in terms of their potential environmental impact over its life cycle. So it's a decision support tool, as I mentioned. So what does this mean? So for example, it can be used for hotspot analysis. So if you have a product, such as you're looking at the production of a battery, you can then use life cycle assessment to identify high contributing flows, high contributing processes within each of the stages of life cycle assessment. You can look at, is the production stage or the use stage, for example, contributing more to the overall impact, which impact categories might be contributing more. And impact categories really focus on an environmental concern. So we will take a look a little bit more into details about this later. Can also be used then for comparative analysis. For this, we have comparisons for alternatives, so alternative materials, alternative products, alternative production processes, where you're trying to make a comparison of option A to option B. But you should take some care with this, because it's not always possible to compare, say, one LCA study on a product to another study that has been done separately, due to possibly a mismatch of methods, different data being used, and this is something we will address a little bit later. Life cycle assessment, then you have guidelines and standards around this. For example, there's the International Organization for Standardization, and they publish standards and review them every 5 years for life cycle assessment. And I believe the last review was done possibly in 2020, with some amendments to these standards in 2006, but that the standards are still valid. And then there's other standards that kind of stem from these. So usually this is the basis of any standard that you're looking at, comes down to the international standards. So this defines life cycle assessment then into 4 different steps. So we have the goal and scope definition, life cycle inventory, life cycle impact assessment, and the interpretation. And there's also then the International Reference Lifecycle Data System Handbook. So this is something where the international standards have sometimes been criticized for being a little bit too vague in how they outline their methods. So the ILCD handbook looks at more specifically detailing different options, different methods that can be used to comply with these international standards. And then there's also the product and sector specific standards. So something that maybe some of you are familiar with would be the Greenhouse Gas Protocol. There's also environmental product declarations and the product and organizational environmental footprint from the European Commission. So if we look into the environmental product declarations, so EPDs, so these are type 3 environmental labels, which means that they need a verified life cycle assessment by an independent reviewer. And they usually adhere to specified product category rules. And some maybe criticism here with the environmental product declarations is that sometimes there has been a variety of product category rules created for a particular product, which means that now you no longer have the comparability. So one way of addressing this was to then develop the product or organizational environmental footprints, the initiative from the European Commission. where they're aiming to really harmonize the methodology and then allow for comparisons across different studies that have applied these rules. So in this case, looking at product environmental footprint category rules or organizational environmental footprint sector rules. What we're going to go through then, I mentioned that there's 4 iterative steps of a life cycle assessment. And we're going to go through these steps and have a detailed look into what consists in each step, and at the same time, looking at how this looks at our case study, where we're focusing on the LCA of residential building. And for residential building, when you look at LCA, there's different phases. So we can have the pre-occupancy phase, occupancy, and post-occupancy phases. So pre-occupancy looks at raw material extraction through to the construction of the building. Occupancy, then the use and maintenance cycles of the building, and finally post-occupancy when you have the final demolition and disposal of the materials. So if we start then goal and scope definition. So goal and scope definition really sets the scene for your LCA study. So you define the overall goal. So what is the reason that you're conducting the study? You also define your functional unit. So what does this mean? So functional unit, you're having a reference unit for which all your inputs and outputs are scaled to, and it should also include the function of the product. So for example, if you're conducting a life cycle assessment for the production of a battery, you might have a unit of per kg of battery, and this then is kind of saying that you're producing this battery to maybe sit it on a table and look at it, because you're not including its performance within this unit. So some ways to then consider also the performance aspect, you consider the function. So what is the function of the battery? Well, it's for storing energy. So then what is the capacity of the battery? Maybe you want to consider. But to do this, then you're considering maybe a kilowatt hour, for example, within your functional unit, and maybe also the lifetime or cycle life for the battery. It also, the goal and scope definition, you define your system boundary. So you cut where you are going to focus your LCA study. So which processes are being included within your study. And you also should explicitly state all methodological considerations. So what are your data sources? What are the data quality requirements? What impact categories are you going to assess? And state all assumptions and limitations of the study. So you're really setting up everything that you need here, which you're going to use within the other steps of the study of the LCA. So if we look at our residential building case study, the goal was to quantify the potential environmental impact of the construction of a residential building. And the building contains approximately 300 apartments, say 30,000 square meters. So the functional unit then is described as the fully constructed building of a certain meter square of floor space. And the impact category that we're looking at is climate change. So I see a question here, what are the impact categories? So these are really focusing on particular environmental concerns. And we will go into a little bit more specifics, particularly around climate change later on. And the system boundary then that we are looking at is actually cradle to gate. So what does this mean? Well, I showed you the idea of the full life cycle of the building, where we have all these different stages. And in life cycle assessment, we also used other terminology such as cradle, gate, and grave. So a full life cycle building, you might have a cradle to grave study, which includes the use and disposal of materials. And here for this case study, we're cutting then at cradle to gate, where is at the area of the end of the construction of the building. So it's preparation for occupancy. So when we look then at the second stage of life cycle assessment, this is life cycle inventory, and this is really your data collection stage. So this is when the data for all the inputs and outputs that you defined within your system boundary that are going to be included are then scaled up as well to your functional unit. And the collection can be divided, say, into foreground data and background data, where you have more product-specific data, and also generic data being used from lifecycle inventory databases. So, however, there are also situations where maybe background data becomes a little bit more significant, so it has an influence on the final result. And then in these situations, you also want to use more relevant data, so maybe more product-specific data for this. And software can be used then to easily track your materials, your emissions, energy, and waste flows, and compile it then into your final lifecycle inventory data. There are also different approaches that I wanted to briefly introduce. There's top-down and bottom-up approaches, including process analysis, environmentally extended input-output analysis, and hybrid techniques. And what this is, so process analysis is your bottom-up approach. And basically what you're doing is you're focusing then on collection of product-specific data, material, energy, waste for the product or system that you are analyzing. And this can be either technology-specific data or also data from databases. However, there are limitations here, because at some point you have to cut the system boundary. And when you do this, you create some truncation error. And then there's environmentally extended input-output analysis. And this uses national average data obtained from economic input-output tables. So input-output tables contain monetary data for aggregated sectors of an economy. And they also represent then the interrelationship of the sectors within the economy. And with this, also you need national environmental accounts data per sector. So the limitations of this are that the input-output tables are highly aggregated, and depending on the country, it can be different levels of aggregation. And the reason being that to keep the data anonymous. The hybrid techniques then look at a combined approach, where the aim of them is to combine the process and the input-output process approaches in a way to minimize the limitations of each. So there are multiple types of hybrid techniques, and I won't get into the details of that, but they cut the system boundary of your process system and your input-output system in different ways. And because of this, you have to be careful about double counting errors. So depending on where you draw your boundary, you need to make sure that you are not double counting an emission within the process system and the same one within your input-output analysis system. And it can also be computationally time consuming. So if we look then at our residential building case study, I have applied a hybrid technique, and some of the data sources then include the data from the Ecoindent databases for production of the materials that are used, as well as for transportation. And also the bill of quantities for the building. So the list of material quantities that are needed is provided by the quantity surveyor. And also the input-output tables for Ireland and the economic accounts data for Ireland. So why Ireland? The case study was actually for a building being constructed in Ireland. So when we look then, like, okay, what are we doing here? So we have our defined system boundary where we have our cradle to gate. So we have our cradle to gate system boundary, and we have collected then all this data for materials, transport, construction, materials and transport data coming from databases, construction data coming from a top-down approach using our economic data and environmental emissions data, and putting this then into inventory data of our emissions and resource extractions. So we have everything being compiled then into our lifecycle inventory data. So the next step then is lifecycle impact assessment. So we have this list of data. Now what? Now we need to interpret it. Now we need to, what kind of impact is it having? So life cycle impact assessment then is done in multiple steps. So the first is classification. So it categorizes this life cycle inventory data into impact categories. So what are impact categories? They represent a specific environmental concern. So some including climate change, resource depletion, human toxicity. And the next step then we have characterization, which really converts this data, so all the input and output quantities, into the unit of the impact category. So for example, kilograms of carbon dioxide equivalents, and you can aggregate them into one impact indicator score. So I see some questions here, and I think some of these will be answered a little bit later, and if not, then we can also go back to them. So I mentioned that there's characterization within this, and so how does this work? Well, you need characterization factors which are derived from complex characterization models along a cause-effect pathway of an emission or resource extraction. So our life cycle inventory data has a list of, say, the cause, and we also need to then have a factor which brings this to the final impact. And how this is done is you have your calculation of your impact indicator score, then your inventory data multiplied by its associated characterization factor, and the sum of everything to give you your final result. So there are also optional steps in life cycle impact category that we won't address today, but these are including normalization and weighting. So yes, I will leave it at that, and we focus then on these characterization factors. So the characterization factors can be derived at either a midpoint or an endpoint. So this is the cause-effect pathway, say that I am stating. So there's the cause, your life cycle inventory emissions data. So for example, these are some greenhouse gas emissions. And you want to know what its overall effect is. So the damage to the different areas of protection, which there are 3: human health, natural environment, and natural resources. So the characterization models then derive characterization factors either at a midpoint location or at an endpoint, which is closer to the effect. The midpoint indicators are not necessarily at the midpoint of the cause-effect pathway, but they occur at a point that after which the environmental mechanism to the endpoint is identical. So we have differences of where this can occur for the different impact categories, such as climate change, human toxicity, metals depletion. And then for the endpoint indicators, I mentioned that they are closer usually to the area of protection. So sometimes it's easier than to understand what they mean. So it's easier to conceptualize because they are closer to this area of protection. And midpoint indicators, though, often have a closer, stronger relationship with the cause. And so that's why sometimes it can be a little bit of a jump to conceptualize what this means in terms of an effect. And because of this, also, it's sometimes considered that midpoint indicators have a lower uncertainty than endpoint indicators. So I want to mention that multiple life cycle impact assessment methods exist, and different standards will have some recommendations on which impact categories to include. So for example, the product environmental footprint, they recommend to include 16 impact categories. And I have here in this figure, sorry that it's a little bit difficult to read, is showing the Recipe 2016 Life Cycle Impact Assessment Method. And you can also find more details here in this paper. And they have then around 17 midpoint indicators, and they also give factors to go from your midpoint indicator to your endpoint point area of protection. So this shows the relationship then with the midpoint to the endpoint. We are at life cycle impact assessment. And for our residential building then, what does this mean? So we are actually focusing then on climate change. So we have in our impact, in our inventory list, a list of greenhouse gas emissions such as carbon dioxide, methane, nitrous oxides. And the midpoint indicator for climate change is actually radiative forcing, which is measured in watts per meter squared. So this is really the net change in the energy balance of the Earth system. So it's usually expressed in watts per square meter, as I mentioned, averaged over a particular time period. So this here is a picture of the greenhouse effect. So what happens? You have your solar radiation coming in. Some is reflected by the cloud covered, some is reflected by the atmosphere, some is observed by the Earth's surface and leads to warming. The Earth then can emit infrared radiation through the atmosphere. It can be absorbed and reflected by cloud coverage. It can be absorbed and reflected by greenhouse gas emissions, greenhouse gases in the atmosphere. So the radiative forcing is really quantifying the energy imbalance that occurs when an imposed change takes place. And we know global warming then is an increase in the global temperature over time, which is being enhanced by human activities. So life cycle assessment then can be used to quantify the potential impact on climate change. And with this, then we have these characterization factors, which are called global warming potentials from the IPCC. So this is the Intergovernmental Panel on Climate Change. And they are derived for each of the greenhouse gases based on their estimated atmospheric lifetime, and also based on their radiative forcing compared to reference values for carbon dioxide. So everything is in reference to carbon dioxide, which is maybe why you are familiar maybe with the term of kilograms carbon dioxide equivalent. So here I have some of the information, but I also recommend that there's so much information on the IPCC site. Showing the radiative forcing, for example, over time for different greenhouse gases, and also the radiative forcing after certain years of emission. So this is used for, I think, the simplistic way to represent the calculation of global warming potentials, where you have the ratio of the cumulative radiative forcing induced over a certain amount of years for a certain greenhouse gas over that of carbon dioxide. For our impact assessment, then we have all of our materials data, transport, construction data compiled into an inventory, multiplied by the characterization factor, and we get an overall result. So the overall result that we have here is around 30,000 tons of CO2 equivalents for our one apartment development, which is around 30,000 square meters of floor space. And this is cutting the boundary from cradle to gate. So I'm going to leave this here and move on to the next step, and we come back to that. So the next step then is interpretation. And this really ensures that the results are consistent with the goal of the study. So here we can identify significant issues. So what are the life cycle stages that are relevant? What processes, what elementary flows, so what resource flows, emissions flows, what choices have we made that are significant to the overall results? And you do a consistency, completeness, sensitivity check. So have the methods been consistently applied throughout the assessment? Is it complete? Are there data gaps? Example, and then you come to your final conclusions and recommendations. And the keynote here is also that it's an iterative process. So what this means is that you can go back to each step as you gather more information going through the LCA and make changes. But the key is also that you should ensure that your results and recommendations that you make at the end are also aligned with the goal. So why are you conducting this study? So everything should be consistent. So this was a very brief and maybe I hope you learned maybe some also interesting details of life cycle assessment. So we looked at life cycle thinking, life cycle assessment, some of the standards around that, and described the steps then of the LCA. And we all now also want to look at and understand some of the key challenges of life cycle assessment.
Okay. I mean, if you want to take some of the questions first, Deirdre, that's fine. Or if you'd like to continue, that's okay too.
Okay, maybe I continue and then answer some of these questions at the end.
Sounds good.
Perfect. So I wanted to just take a look into the key challenges of life cycle assessment. So one thing is we have variation in life cycle assessment results across studies. So if we look at, for example, lithium-ion battery production, so this is the production of a battery, so cradle to gate, and there are various studies that have done reviews on different life cycle assessments, and you can see that there is a result of a difference of an order of magnitude for kilograms of CO2 equivalent per kilowatt hour. But why? So this range really depends on which battery chemistry you're looking at. So in our battery production, we could have different cathode materials, for example. Which production scale? So this is also an interesting point. So was the data collected from laboratory scale and it's in its very immature technology, or is it a mature technology that's produced at a large scale and the data was used from this? And there are also different data and modeling assumptions. So the important point here is really that comparability of studies, also you really need to understand what methodological considerations and limitations are behind this study and go into a little bit deeper to determine why you might have some variations as opposed to just saying that one is better than another. So you need to dig a little bit further to see what differences and why. So some other challenges of LCA then are data availability. So data can be confidential and therefore difficult to acquire. There can also be a lack of data. So there's no data on a production of a particular product or chemical, for example. As I mentioned, comparability across studies. So are two studies actually comparable? And this comes into the next point too. Can we come to a consensus on harmonizing methods? So if we apply the same methods and we have some way of then improving the comparability across products here. And there's also interesting in transparency of reporting. So this is an important point as well because it leads to knowing what was done within the study. So what methods were applied, what assumptions, what limitations, what are the data quality sources. And in reporting this, we should also then have how can the study results be used and how can they really not be used? So, for example, if you set out for a specific goal and have a specific result according to this goal, it's not necessarily applicable in another context. Another challenge I wanted to just bring forward, because I think it's very interesting as well, is this idea that you can have variation across software, LCA software. And so what does this mean? Well, okay. So we have, in a very good way, we've had rapid development of lifecycle inventory databases, lifecycle impact assessment methods, and software in parallel. And that means that sometimes there is a disconnect in which nomenclature is used across each, and there isn't yet a harmonized way to do this, and so therefore can lead to some mismatches and uncharacterized flows. So for example, and I also refer you to this paper in the International Journal of Life Cycle Assessment. They describe four situations that you can have when you are looking at going from the lifecycle inventory data and connecting a lifecycle inventory assessment method. So situation one here, we have inventory, so an elementary flow. So this is an emission such as carbon dioxide, resource extraction, but it's not just this information. So often you have this combined with other information such as the compartment, what it's being emitted to, so atmosphere, water, soil, as well as the unit as well. And it's classified into this life cycle impact assessment method. And if you have a match, it's classified and then it's associated, paired with its associated characterization factor, and you have a result. And this is a good situation. But then there are also other situations where you have uncharacterized flows. The second one here is you have an elementary flow in your inventory. You have a characterization for this flow, but for some reason, your inventory data is not really talking to your impact assessment method. So they're using different nomenclature, and so it's missed and you have an uncharacterized flow. And the other two situations then are the impact assessment method does not define a characterization factor for a certain inventory data, even though it exists and is classified, or it has a characterization factor for a particular emission, but this is actually not quantified in our inventory data sets yet. So then this can also lead to uncharacterized flows. So this is a very interesting research area, and they're looking into harmonizing the nomenclature for this. So there's a lot of work being done in this. And also, as in this paper here, they're looking at ways to then processes to map uncharacterized flows, because it's not very easy to do and it's not always very obvious when this happens. And an LCA practitioner can't always identify this, depending as well if they're depending on which software they are using. So the last thing that I wanted to introduce is then uncertainty management in LCA. So unfortunately, uncertainty is still ignored in lifecycle assessment studies. However, it arises everywhere. So yeah, in the data, the models, as well as the decision made in the study. And we know that LCA studies have large amounts of data. And we know that with information regarding uncertainty, you can actually make better informed decisions. So we have seen that it's not common practice in LCA. So in a study done in 2020, they looked at the total number trends in the total number of life cycle assessment studies, as well as those that are including uncertainty. And we have a steep trend here of increase in LCA studies, and I think even steeper now. This ended at 2017. And we have quite a maybe flatter curve when it comes to including uncertainty. And I think this is where some things can be improved. So the reasons for missing uncertainty then, lack of resources, time and budget. So LCA studies are already very time consuming, data intensive. Lack of knowledge of how to do it, and lack of a standard method or procedure. So this is kind of where the area of my PhD had focused. So we look at this result that we had from our residential building case study, and you may have thought that it was strange that I presented the result in this way on quite a curve here. And the reason for doing this is that really we want to move from these pinpoint values to distributions, where we see also that we're including uncertainty. So I'm not going into details today about how to include uncertainty management in LCA, but this is also within this paper, so you can have a look into more details here if you like. And we included some uncertainty in the data, some uncertainty in the choices, and using Monte Carlo analysis, then have a distribution for the final result. And the idea is that uncertainty management also doesn't stop here. So it's great to quantify it, but what we really want to do is reduce it. So the study also looks at then how to rank and reduce uncertainty. So I also wanted to open up a point here. We discussed some challenges of life cycle assessment around data availability, around harmonization of methods, etc. And one thing that I wanted to pose to the audience is, what do you think about, should lifecycle inventory data be openly available? So I think this is opens up quite a lot of different things. So it could be, yes, it should be openly available. No, it shouldn't, somewhere in between, because So I just wanted to first just pose this question to you. Should LCI data be openly available? And please enter your thoughts in the chat, maybe in one sentence or two if possible. Yes, it should. Nice. Okay. So we have also yes, a peer-reviewed way. And I think that this brings up a point, because we also want to, if we have openly available data, we also want it to be kept and maintained to a certain quality. Somewhere in between because of confidential issues, and this is also for sure a very good point, because we exposing everything, is it a good idea, is it not, but does it help us move forward, but does it not? And for sure it saves time, so this is so holding open data to high quality standards and assurance, yes, I agree. And openly available LCI data saves time. That's nice. Because yeah, there's challenges when it comes to collecting data. So thank you for your thoughts around this. And this is also something that is debated and discussed. And I think as we look into harmonization of methods, it's going to become more of a point. So yes, so this is, I wanted to just maybe lastly, just look at the life cycle assessment. Really, our overall goal is to improve the reliability, robustness, repeatability of life cycle assessment results. And there's a lot of progress that is happening in this, but there's things that can also be done. For example, the LCA practitioner looking to include an assessment of uncertainty. So it was mentioned here also some sensitivity analysis, scenario analysis can also be including this. So being sure to include these things and transparently report this also to the final decision makers. And data providers to LCA databases then include quantified and qualified uncertainties, and also be transparent about the limitations and how the data can be used and how it cannot be used. And finally, decision makers then look closely at the LCA results and also ask for transparent uncertainty information. And by doing it this way, it also means that more people are going to be including uncertainty analysis, so not just sensitivity or scenario analysis, but also looking at differences in uncertainty within their LCA. So the good news, lots of progress is being made here, and there's lots of things to come. I also wanted to just provide two different open source LCA software. So we spoke about open data, so there is also open source LCA software that you can use, such as OpenLCA. And here you also have the ability to do some Monte Carlo simulations and some uncertainty analysis, sensitivity analysis. And also there is Brightway 2. So Brightway 2, however, requires some knowledge of Python. So if you're not very excited about coding, then it might not be the software that you start with, but it's also an option that is open source. And that is then everything. And I hope, yeah, you learned some things and took away some things from today. So thank you very much.
Great. Thank you. Thank you so much, Deirdre. That was great. I think it was a really, well articulated presentation and very insightful. Are there some questions in the past that we have not yet answered?
I think so.
Yeah. So should we go through them? So let's go through a few that I think we missed. How do you how do you spot greenwashing in an LCA, and what should you look out for?
Yes, that's a very challenging question. I think very good question. I think going to looking at the methods that were applied, looking at the quality of the data that was applied, looking at the transparency of the limitations and assumptions of things that were reported. So in terms of this, really being, sorry.
你有冇瞓一齊呃啊？
Sorry, can you please mute yourself, Edwin? Yeah, thanks. Sorry, go ahead.
Okay. So yeah, it goes down to looking into the details that are provided with it, and not just believing the claim, but looking down how did they come to this conclusion.
Right. Okay. So you're basically saying to review the data a little bit more to spot greenwashing. Is there anything else, anything specific people can do?
So, I mean, no.
Okay.
Yes.
Okay.
But I mean, making sure that the methods are followed, the standards are followed, that they have done these, and that the limitations are clear, because even LCA studies have limitations. So if they're making very big claims, there has to be a reason and support for this, not just a claim without any support. So just looking really into, okay, great, this is what you come up with, but why, and where's the support for it?
Yeah. We then have a question from Sunil, who says that isn't LCA a complicated approach for a consumer model economies? So where GDP and profits are the key metric of progress, there's going to be a conflict of interest stunting any meaningful progress with just discussion and reports.
Okay. The long question.
Yeah. Sunil, do you want to, yeah. Sunil, do you want to explain that a little bit more?
Yeah, thanks, Namrata. Like, I just wanted to check, basically, see, the current economic models are always, you talk about GDP is fallen, or, the profits have not gone up and people are being laid off. So the key metric of a progress measure is creation of stuff. Creation of things, and manufacturing is the driver of growth. And in such an economic model where consumerism is at the core, we are doing LCA, which is good, which is important actually, to ensure the right materials are used. But that kind of, this model itself aggravates the problem and increases the complexity of doing LCA. Whereas if you change the model, you can apply a simpler LCA. I hope I make sense there, because yeah, I know it is a difficult thing to do because countries are so used to, all these models and all, but I'm just saying, the other side of a perspective, different perspective.
Yeah, okay. I think I understand a little bit about what you're saying, but maybe just as an additional point, there's also the idea of including, and there's now standards coming about including, say, social life cycle assessment, life cycle costing, as well as from the environmental side. So this looks at maybe incorporating all different aspects as well.
Okay. Then we have a question from Dragana. Can you elaborate more on GATE? Because people are typically familiar from cradle to grave, but GATE is a new concept. So can you elaborate a little bit more on that?
So by GATE, it stops, say, usually before the use phase, but you can also have, now this is going to get maybe confusing, like gate-to-gate processes. So this is maybe the production of one process, not including its extraction from raw materials and not including its use or maybe further manufacturing, but you are setting your boundaries at a certain position along with the life cycle.
Right. So I think it is a complicated topic, right, Deirdre? I think just, so Dragana, maybe post this session, we can walk you through more about the GATE if you're interested. I think we have another question that just came in because about, from your experience, what is the cost, time and effort difference between cradle to gate versus cradle to grave?
I think it depends on how complicated and how maybe detailed you are including your disposal scenarios. So I think when this is done well, it is also just as intensive as your product and your use. when this is maybe highly unknown, and as an afterthought, maybe to include something and you have some scenarios set out, maybe it maybe is not as specific as it needs to be. So I think it depends on your overall goal of your study, and it depends on where you're focusing.
Right. Another question from Ida, where she asks about, please explain more about endpoint impacts. For example, 3 different groups of global warming potential, such as terrestrial, human health, and freshwater. How can they be explained?
Okay, so different group of global warming potential in endpoint categories. So this I'm going to have to get back to you because I don't have specific details of every impact category, but I know that there's also the paper that I referenced as well for the recipe method, which I think would give also lots of details here. So it might be interesting for you to look at that.
Right. And then the last question that Anne-Marie just asked, is circularity becoming a bigger focus in LCAs?
So a bigger focus, I would say yes, it's a focus and it's something that is always discussed, and it depends, again, I guess, the context in which you're applying the life cycle assessment. So if it's for looking at improvements in circularity, and then this is in the context of circularity, and then you try to align it as such. But in general, whether or not it's always considered or never considered, I wouldn't really have a good overview of this.
Okay, great. So in the interest of time, I'm going to end the questions here. Thank you so much, Dr. Deirdre. It was a fantastic session. You can see with the engagement how interested people are in the topic. And we'd love to have some follow-ups. If people are looking for specific information about LCA, feel free to write to us and we'll connect you to Dr. Wolf. But thank you so much for tuning in today. We at ShiftEco and the Umbrella Institute are constantly doing sessions like this to help us discuss further about key topics in sustainability. I'm quickly putting in the chat also the next event that we are conducting. It's basically going to cover basics of carbon emissions. It's going to introduce you to the different scopes, scope 1, 2, and 3, and give you a framework on how you can kind of calculate your emissions. So stay tuned, and we look forward to seeing you in our future sessions. And if there's something specific that you want covered or topics that you're interested in, please feel free to either write in the chat or write directly to us at ShiftEco, and we'd be happy to include these topics in future sessions. That's it from me. Thank you so much again, Dr. Wolf. We really, thanks a lot for being here today.
Thank you very much for having me. It was great. And thank you everybody for taking the time to attend. And I hope you had some takeaways from today.